Okay. Hello, everyone. Welcome to the International Methods Colloquium. I am Justin Essery, an Associate Professor of Politics and International Affairs at Wake Forest University. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and Springer Publishing, and previously sponsored by Rice University and the National Science Foundation. We have a lot of speakers this week, two groups. The first group is Soren Jordan of Auburn, Hannah Paul of CU Boulder, and Andrew Phillips, also of CU Boulder. And our second group is Jared Edgerton of Ohio State and Grant Buckles of Gallup. So Springer's new series, Textbooks on Political Analysis, is accepting submissions for applied text on topics in political methodology. I've taken over editing this series, so you can speak to me or Springer editor Lorraine Klimowich for more information about the scope of the series and how to submit a proposal, and I'll post a link with that contact information in the Zoom chat window after this introduction. We are currently hosting a special series of presentations originally slated for the 2020 annual meeting of the Midwest Political Science Association that was canceled due to the outbreak of COVID-19. Each of these sessions will host two talks lasting 20 to 25 minutes each, followed by 10 to 20 minutes for Q&A. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window, and you can ask a question at any time, but we will hold all questions until the end of both presentations. A link to the presenter's slideshow will be available in the Zoom webinar chat window so that you can refer to it throughout the presentation, and I will post those links right after we get started. So our first presentation is going to be from Soren Jordan, Hannah Paul, and Andrew Phillips, and their talk, as you can see, is entitled "How to Cautiously Uncover the Black Box of Machine Learning Models." Welcome, and thanks for being here.
All right, thanks everyone. So I'll just jump right into it. This is some tentative work that we'd like to show you all today. We have 3 or 4 claims in this paper. The first one is noticing that scholars are increasingly using machine learning techniques for not just prediction, but also causal interpretation, especially in regards to the effect of certain predictors on their outcome of interest. And one of the issues with this, of course, is that these machine learning models, despite all their flexibility, are actually really hard to see. In some ways, they've been critiqued as a sort of black box approach. And so pretty much the most common way to visualize these results are through actual plots. And these are becoming more popular, as we'll see. So what we do throughout this paper is we first provide an overview of some newer plots. So some of these plots you may have heard of, other ones probably not. And with these new plots, despite their advantages from previous plots, there also are newer issues. And so the second part of our project is identifying several downsides that we found and proposing some tentative solutions. So we'd especially like your feedback on those things that Soren's going to talk about. Okay, so the first thing we did was see what are people actually doing in political science. So we did a really simple literature search of the term machine learning in top journals, and we identified 65 papers. One thing we noticed is a lot of people are using machine learning models in the form of when their data are text as data. A lot of people are using tree-based models, so things like random forest or other types of regression trees. Neural nets, slightly less popular. And so that was just like a cursory look at what's going on. The 2 up top are a little bit more relevant to what we'll talk about today. The first one is at the very top of this figure is the variable importance plot. So that's a way of telling which variables actually matter to the model, since in these machine learning models, you have lots and lots of predictors. And we won't really talk about those today because they're pretty common. The second one down below, though, the partial dependence plots are where we'll start. So we can already see that some people, like less than 10% of these papers, are using these sorts of visual aids. These are definitely becoming more common, so these appear in more recent papers. And so this is essentially where we'll start. So what we're going to do is let x sub is be our feature of interest, the variable that we care about. We'll let the bolded x sub ic be all the predictors in our model, not including the one that we actually care about. And then the next thing we're going to do is estimate a supervised machine learning model. So for our applications today, we use a random forest, but you could use any of these other ones as well. So from that model, we're going to get a prediction function. We'll call that f hat of x sub is and x sub ic. And our next step is, given our model, how can we visualize the effect that the x variable that we care about has on y? So the most common way to do this is through what are called partial dependence plots. So these have been around for about 20 years now. And what we're really doing, I won't, in the interest of time, walk through all these equations. But effectively, if you look at equation 2, all I'm doing is setting my x variable that I care about to some particular value, keeping all the control variables at their actual observed values, running it through my model. So this is using the training data set, running it through my model, getting a prediction, and then averaging over all of those predictions. So number one is how we think about these partial dependence plots. Number two is what actually happens in practice. So this is a nice example. This is a toy data set that we'll kind of go back to a few times. So this is just using 2016 ANES data. We're trying to predict the GOP thermometer, and our X variable that we care about is whether the respondent thinks that the income gap is larger today than in the past. And so really, you can see in the center table here, what we're doing is keeping all the control variables at their observed values, setting income gap to -1, running it through the model, getting a prediction, and then taking the average. And so in this case, the average GOP thermometer setting income gap to -1 was about 45. Same thing, right? If I want the income gap to be 2, I would do a similar thing here. So in a way, the partial dependence plots are really nice because they're averaging over the effects of all these other variables in our model. So the partial dependence plots are relatively common, but they're subject to a particular critique that was pointed out by Goldstein et al. And that's really that by showing the average prediction functions, the partial dependence plots might be overlooking really important heterogeneity. So all they propose is just plotting those individual prediction function curves. And the names of the plots in the paper today are kind of fun. This one's called a individual conditional expectation, or ICE plot. So this is all it looks like. So the yellow, black, bolded line is the partial dependence plot. And the light shaded lines are the actual individual prediction functions. So in this case, we can see that overall, most of these individual lines are pretty much following what the PDP says. The dark circles are the actual observed value of the X variable. So in this case, it's government action on climate change. So there's not much going on here. This is not always the case, as we'll see. So the Goldstein et al. Proposed a bunch of other variants. One of them is something called a centered ICE plot, which pinches all of the curves to a particular point, typically in the first percentile. So it'll be on the left side of the plot. Something called a derivative ICE plot, which is just the rate of change of those ICE functions. And then the last one is you can actually color these ICE lines by a particular factor variable if you think that's possibly interacting and causing the heterogeneity. So just to show you some of these, that was the climate change slide from a minute ago. And now all we're doing is centering them through 0 all the way on the left of the axis. So again, here, not too much heterogeneity going on. This is the de-ice, so the rate of change. And again, we can kind of see it's moving down as income increases. The rate of change in terms of GOP thermometer is moving from positive to slightly negative. And the last one is a colored ice plot. So in this case, we take our ideology measure and we color it by whether you think the income gap is getting larger or smaller. And on the right plot, we see the red lines. Those are people that believe the income gap is staying the same or shrinking. And it looks like for those people, the ideology has a negative effect on GOP thermometer. And for the blue dots, it's a little bit less clear, or maybe even positive. So the problem with the partial dependence plots and the ice plots is this assumption that X sub S is uncorrelated with all other features. And the issue here is that we're using the entire marginal distribution. And why is that bad? These are counterfactuals that may not actually exist in the data. And there's been critiques in regular parametric models about doing this. And it's even worse in machine learning just because these models are so flexible. So here's a nice illustration of, I have two predictors, X1 and X2. I care about the effect of X1. My issue, though, is I'm looking at that entire marginal distribution of X2. So a solution is something called a marginal plot, which is not a great name because it actually uses the conditional distribution of our control variables. And I'll just show you a plot because I think it makes it a lot easier to see. Right, so now instead of using that entire marginal distribution of X2, I'm just zooming in to the actual values of X2 observed when X1 is equal to 0.3. So this is a nice solution. Soren's going to take over from here, and as we'll see, there are bigger issues to this as well.
So M-plots might also suffer from omitted variables bias, in that a correlated variable to our predictor of interest, X sub S, might be causing the observed effect in the M-plot. And we can get around this challenge by considering accumulated local effects plots, or ALE plots. ALE plots accumulate differences in the changes in Y in small, defined as integral distances over a range of X sub S. They're actually operationalized by partitioning X sub S into K regions and comparing the changes in predictions generated from fitting X sub S at K to X sub S at K plus 1. These effects are accumulated across the range of X sub S and centered such that they are mean zero with respect to the marginal distribution of X sub S. This is way easier to see visually. So if we advance one, we'll be looking at a fairly normally distributed variable. So if we pretend this is our variable of interest, X sub S, our first job is going to be to split this variable into K categories of interest. The next, and here they are. So X sub S has been partitioned into K equals 10 categories. More generally though, K right now in the literature is assumed only to be equal density regions, so quantiles. K is user defined with no validating procedure for optimization. And K can also be changed programmatically without informing the user in cases like count or categorical variables. And we'll return to these criticisms in a moment. For now though, let's just pretend that our breakpoints that we're interested in are categories 2 and 3, which are now highlighted. The way an ALE plot is going to work is by taking all of the observations in the region highlighted and fitting them with the value of X sub S at the lower breakpoint, and then refitting them with the value of X sub S at the upper breakpoint. And these changes in predictions are then compared as the ALE effect moving from X sub S at K to K plus 1. The ALE effect over across the range of X sub S is therefore actually calculated at the K breakpoints. And a line is then drawn connecting the calculated ALE values across the breakpoints. We appreciate this as a new way of thinking about the effect of X sub S on Y from a black box model. And moreover, the ALE plots can be drawn from any model with a prediction method, which is useful. However, we present or suggest at least 4 extensions. The first is that the ALE plot is currently drawn what we might call naked with respect to both the distribution of X sub S and the K breakpoints. And this nudity is pretty objectionable, given that the naked ALE plot makes it look like the estimates of the ALE effect are generated from equivalent amounts of data across the range of X sub S. To better illustrate this point, consider an AL plot drawn. This is from the AL plot package, from a neural network with the sinusoidal effect of a long-tailed skewed x sub s on y. Here, k equals 25 breakpoints. And looking at this plot, we might think that we have this nice calculated effect across the entire range of x sub s, or reconsider the plot with the actual breakpoints drawn as well as the underlying density of the variable. Now, looking at this, the AL plot generates really nice and tight predictions as x sub s changes across its range in the lower clump, closer to where the mean is of the distribution, away from its skew. However, the AL plot draws over 30% of the range of x sub s using just one set of comparisons, the second to last and the last breakpoints. And otherwise instructed, the AL plot is actually going to automatically take the minimum and maximum observations on x sub s as the first and last quantiles to be fitted. And that behavior might be undesirable as all of the observations within that quantile will be fitted with this extreme prediction comparison, where they are to where the minimum and maximum of the variables are. So if we have outliers in our data set, this could cause undesirable behavior. And at worst, the plot itself is going to suggest that an equal amount of weight is given across the entire range of x sub s. Let's think about k in more detail. Like we mentioned before, k is currently a user-defined number of quantiles to consider. However, this value can be dependent on the number of categories in x sub s, and that's not really conveyed to users. As we already saw, even when k is applied to truly continuous variables, adjusting its value doesn't really increase the precision of the AL effect equally across the range of x sub s. For instance, observe the effect of doubling the number of breakpoints on the same x sub s variable with a sinusoidal effect, this time from k equals 25 to k equals 50. In the upper plot, we see the effect of having 25 breakpoints, in the lower plot, 50. And virtually all of the breakpoints that were added are in the same region, which is close to the mean of x. In the very far right part of the tail of x sub s, over 20% of the range of that variable is still being predicted for the AL effect with the same number of comparisons, which is 1. And again, we're not necessarily arguing that this is problematic behavior. We know that the density of our variables occurs in certain places. We just want to bring attention to this fact to the user, who might very well believe that he or she is adding twice as many comparisons equally across the range of that variable, but instead might be actually trading off the density within each quantile to add breakpoints in approximately the same place. Which leads to an even broader question. Is quantiling even the best way of breaking up the data? Because we can imagine alternate methods. For instance, binning the data like in a histogram. Let's see this distinction in practice. The top plot here shows an AL plot drawn from dividing the data into bins rather than quantiles. Notice how the breakpoints map to the bins of the underlying histograms. The bottom part shows the AL plot drawn from dividing the data into quantiles. In the top, there's less data in the final bins, but more comparison sets and breakpoints to use to draw the AL effect. In the bottom, an equal amount of data are in each region, leaving a large chunk of the line drawn from very few comparisons. We raise these questions because there are currently no answers. We're developing them. We're working on a way of a cross-validation method to optimize the number of k breakpoints to use, as well as an investigation of the circumstances under which bins versus quantiles are the most appropriate. We can even imagine k is not being fixed, and the AL plot is being an average across multiple sets of predictions from different values of k and placements of the breakpoints. Our goal here is just to resolve these questions in a way that leaves black box model users well informed about the estimated effects of their models. One thing we have worked on extensively, though, is AL effects with categorical predictors. Since there's no order to the categories, AL is naturally impossible because there's no obvious replacement category whose value should be swapped and whose predictions should be compared because there's no category to move from k to k plus 1 in a natural order. Apley and Zhu, the original authors, cleverly created a surrogate ordering by comparing the similarities of the categories through their similarities on the other observed variables. These similarities are then ordered by principal components to try and generate an order to the categories. We wondered, though, whether there was a reason to limit the AL effect to just one set of comparisons, given that the order itself is empirically calculated. So instead, we implement a kernel-weighted average of all of the comparisons possible in the categorical data set. The kernel weights use the calculated principal component similarities that the original authors calculate, and then weight those similarities on their principal components distance by a cosine kernel weight function according to the formula shown. Finally, we generate all sets of compared predictions, replacing the observations in category K with each of the other categories and seeing how these predictions change. The categorical AL effect then is the kernel weighted average of moving from K to any category that's not K, Intriguingly, we can also order the categories on the plot itself by their calculated similarities. So we can get a sense of which categories are the most similar. And consider this as applied to the ADS example Andy introduced, this time considering the categorical predictor marital status, not married, divorced, married, or widowed. The top is the usual L plot. And here the comparisons are only between adjacent categories, imagining the space between them as the breakpoints we drew before. Our innovation is the bottom plot, where we show graphically how similar the categories are to each other. We can see that the blue category, not married, behaves very differently from the other three. And the size of the bar reflects the kernel weighted average of being in that category versus any of the others. So the effect of being not married versus any other category in the random forest model is to lower feelings towards the GOP by about 0.15 points, which is a very small effect. The effect of being widowed is to increase the feelings by about 0.2 points, the green bar. And the kernel weighting ensures that the information from the categories between widowed and married is given more weight than the information from comparing widowed and not married, as widowers and married folks are more alike on the underlying similarity measure, as opposed to the other categories. So the comparison is more appropriate. So we can use these plots in new and interesting ways. And Hannah's going to apply that to a real data example.
Okay, so for our applied example, we pulled data from Shea Streeter's 2019 piece in the GOP that examines the racial disparity in police killings between Black and white individuals. We replicated the random forest model from her analysis. The outcome variable here is a dichotomous measure of whether or not the decedent was non-Hispanic white, which is coded as 1, or Black, coded as 0. So in choosing the predictors for our plots, we selected the two most important variables from the random forest model, the first being a continuous predictor, which is age of the decedent, and the second being a dichotomous predictor, whether or not the decedent was suicidal. So for this first plot, along the x-axis, you'll see the actual values for age of the decedent, and the y-axis is the predicted probability that a decedent in a police killing will be white and not Black. This plot is telling us that of those killed by police, individuals who are older are more likely to be white than to be Black. So we're seeing like a fairly large change in predicted probability here. Age seems so important that at low values of age, our best guess is that the decedent is Black, while after about age 40, our best guess is that they are white. So remember, like Andy noted at the beginning of the presentation with PDPs, this is the effect of age in this circumstance while averaging over the effects of all of the other predictors. So next, we're going to look at a couple ICE plots. On the left is a centered ICE plot, and then on the right we have a standard. So let's start on the left one. So here we're looking at the individual predictions using only 5% of the data for visual clarity. And the dark line in the center that's sort of highlighted in yellow is the partial dependence plot. The dots are showing the observed level of age for the individual. So the centered ICE plot is useful for looking at patterns of heterogeneity. Again, like the predictions don't really make sense here since they've been pinched on the left side, which is the convention with these plots. And it looks like age could be conditional on some factor if we look sort of like the lower right quadrant. And when we look to the plot on the right, the standard ICE plot, that possible heterogeneity becomes a little bit more clear. So this plot is giving us the predicted probability that the decedent is white rather than Black. And we see that a lot of the PDP effect is coming from the cluster below that PDP line. At the top, age doesn't really seem to matter as much. So there's a lot more going on in the slope of the predictions below that line, suggesting that there's an important interaction to be discovered, which we are still working on discovering. So for the final portion here, we're going to compare PDP plots against the ALE plots to see how similar or different the effects of age are, and then for our second variable. So like Annie said earlier, if there's a strong correlation among predictors in the data, which given this data set, we think that's pretty likely, this could lead the partial dependence plots to produce incorrect predictions. So on the left here is that partial dependence plot that we just looked at a couple slides ago. On the right is the ALE plot, which shows us a local estimate of the prediction, which ends up being a marginal effect on the predicted probability of decedent race. And this is looking pretty similar to what we saw with the PDP. The effect is smaller, likely because we're using the conditional distribution rather than the marginal. And although age is probably correlated with other predictors, the effects are not interactive to the point that we cannot trust the PDP. So that's good news. For this second comparison, we are looking at the effects of whether or not the decedent was suicidal on the probability that the decedent is white and not Black. So in the plot on the left, we see that of those that were suicidal, the predicted probability that the decedent was white is over 60%. And for those who were not suicidal, the predicted probability drops below 50% to about 40%. The ALE plot on the right shows us the marginal effects of being one category relative to the other. So that's why we're seeing the symmetry on either side of the zero on the y-axis. And if the decedent is suicidal, it has a marginal effect of 0.02 on the predicted probability that the decedent is white and not Black. So this is telling us that the decedent being suicidal versus not doesn't seem to really matter that much. Whereas in the PDP, there's like about a 20-point difference. And since there are a lot of other factors that are probably correlated with being suicidal, it could be that this big difference is because of that, or there could be other factors that are having an interactive effect with the suicidal predictor. But the takeaway here is that if we were to just look at the PDP, we would think that being suicidal makes a big difference in the probability that a decedent is white and not Black. However, the ALE plot does not support that interpretation. So in conclusion, like my co-authors mentioned earlier, this is our preliminary work trying to introduce some of these newer machine learning plots to political science. And as we've discussed, there are some significant issues that come with using these plots when using certain types of data that are pretty common in political science. And so we are working on developing some of the best practices on how to deal with those issues. Thanks for your time, and we look forward to your feedback during the Q&A.
Okay, thanks very much for that presentation. Our second presentation will be from Jared Edgerton of Ohio State and Grant Buckles of Gallup. They're presenting a talk entitled Forecasting Rare Events, a Two-Stage Approach. Guys, go ahead. You might need to unmute your microphones.
Hi, everyone. Thank you for joining us for the presentation. So we have three objectives with what we're trying to do. So first, we want to demonstrate that public opinion data can be used to forecast political events. And the public opinion data we're using is the Gallup World Poll data. I'll give some details on that in a minute. Second, we want to introduce some image classification techniques to predicting political events. And third, we want to provide a framework for predicting rare events. So the three dependent variables that Brent and I are interested in is civil war onset, terrorism, and coups. And we selected these dependent variables for a few reasons. First, these things can be very dangerous to civilians. So more people have died in genocides and civil wars during the last century than homicides and other crimes that were related. So if we have a better understanding of where these events are likely to take place, we can help maybe save civilians. The second reason is that civil wars, terrorisms, and coups are very costly for government. Annually, the United States spends $300 billion on counterterrorism efforts. And if we had a better understanding of where these terrorist attacks were likely to take place, it would help us allocate resources better for counterterrorism efforts. There's some political science research currently that tries to forecast conflict, and most of them use random forest, for example, that we just talked about. And what Grant and I are doing is extending this literature to incorporate some ways that image classification uses to increase their sample size for rare events. So before we get into that process, I just want to talk about the Gallup World Poll data. It's over 2 million responses from 168 countries. It's the most comprehensive global time series for public opinion data that's available. And there's also micro-level data on public opinion for things like religion, health, it's not mentioned here, but also business and corruption data. So here are 3 dependent variables that Grant and I are looking at. And what I wanted to illustrate with this plot is that there's a high level of class imbalance. And that's class imbalance is this idea of very few true positives and a lot of true negatives in the data. And so we're going to focus for the remainder of the presentation on major terrorist attacks as our dependent variable. And the reason for that is actually the other models are still running on the supercomputer. So we just have results for the major terrorist attacks. So for our model, 5% of the outcomes were a terrorist attack and 95% were no terrorist attack for our forecasting. And this can create an issue for testing models because we can achieve a high level of accuracy with sort of a meaningless model. An example of that would be, I could say 95% of the time, there will be no major terrorist attack. I'm sorry, I could say that there will be no major terrorist attack and I'll be correct 95% of the time. But that's not interesting for prediction purposes because it's really just a reflection of the class imbalance. So there's 3 common approaches that we found that people typically use to address class imbalance, and one is upsampling or downsampling. And that's this idea of taking your data and artificially increasing your true positives by just randomly selecting true positives and adding them to your data set until there's a 50-50 break. The second thing is downsampling, where you randomly delete true negatives till there's a class balance. You can also use testing and training data and cross-validation and testing a few models. We're going to do some of that in our presentation. And so the 2 things that we want to adapt for forecasting rare events are adding noise to your true positive data for upsampling, and then a 2-stage classification approach. So I worked on a project about a year ago to identify true bomb craters in a village in Cambodia. We were interested in identifying bomb craters because unexploded ordinances in Cambodia have a really negative economic impact because farmers are afraid to till their land if they think there's unexploded ordinances. And we know where these bombs were dropped because of declassified Air Force data. And so what we were trying to do is find where we see bomb craters, where we know they're dropped, and then where there should have been bomb craters where we know bombs were dropped. But an issue for our classification process was it was hard to find true bomb craters in the satellite image for our testing and training purposes. So what we ended up doing was artificially increasing our number of true images by adding a little bit of noise to each of them. And so I have like 4 examples of bomb craters here, and then 4 examples of the same bomb craters with just a little bit of noise. And this issue sort of addresses overfitting with our data, where we're not overtraining our image classification on the few true bomb craters that we actually have. The second thing we did in this project was we ran a 2-stage model. So in the first stage of the model, we identified candidate bomb craters, and that was anything that looked similar to a bomb crater. And then in the second stage of the model, we separated the true positives from the false positive candidates in that. And so on the top row, we have the same bomb craters that I showed before. And on the bottom row, we can see other candidates that were part of the second stage model. And that's an example of a pond, a house, a forest clearing, and some trees. So in the second stage, we separated those false bomb craters from the true bomb craters. So we're adapting this process to forecasting political events. And the first way we did this was something called permutation upsampling. And what we did is we deleted between 5% and 50% of our observations in the upsample, and then randomly replaced it with a value from the same column. So on average for the terrorism forecast, we see about a 3% change for areas where there was a terrorist attack, and about a 1% change for areas where there wasn't a terrorist attack in our random replacement for upsampling. And this was for survey responses on how afraid a respondent was of a terrorist attack happening. The second thing we did is we adapted the 2-stage image classification process for what we're doing. It was actually really straightforward what we did. We used an elastic net in the first stage to identify candidates or areas that might have a terrorist attack. And then in the second stage, we ran a random forest to separate the candidates from the true positive. And this is just a little example of it where we separate out Iceland in the first stage, and then we would separate out Tunisia in the second stage. To evaluate our model, so we think about these 4 issues: false positives, true negatives, and false negative. And accuracy is often used as the primary metric for how well you're doing. But it's, like I said before, it's not that meaningful for an analysis like this because you can achieve high accuracy with just always guessing something won't happen when you have class imbalance. So the 3 measures we're actually going to use are recall, and that's your true positives or all positives that were detected. Precision, which is your true positives of your true positives and true negatives, and then an F1 score. An F1 score is sort of this idea of balancing your precision and recall. It's bounded between 0 and 1, and this measure is typically used to see for rare event forecasting. And the higher your value is, the better you are predicting rare events. So then this is our two-stage process compared to elastic net and SVM and just a random forest. And we could see when we permutated the values with 50% random replacement, that was the best for our two-stage process. And we get, it outperformed the SVM, the elastic net, and just a regular random forest for the F1 score. I also just wanted to highlight that some of our, the Gallup data that was used for, that had a lot of importance for forecasting, and if survey respondents said they were very afraid of terrorism, their area was more likely to have a terrorist attack. It's pretty intuitive. The only weird one that popped up was the proportion of household children that live at home. That was seen as an important variable for the second stage in our model. So as far as next directions go, we have to run additional classification techniques to just see how the two-stage approach compares. We're also trying to reduce the rate of false negative, and I need to finish running it on civil wars and coup data. So thank you.
All right, thanks very much for that presentation. So at this point, all our presenters are available to take questions from the audience, and if our three previous presenters want to reactivate their cameras, yeah, great, thank you very much. They're all available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And while we're waiting for questions to come in, I'll ask some of the questions that I had. So first, for the Edgerton and Buckles presentation, you know, there's always a little bit of voodoo when you're adding data to, I should say, adding simulated or altered or partially processed data into an analysis. So the analogy I think of immediately is missing data imputation, where we don't know something and we essentially take a guess and put that in there. But we reconcile ourselves to that because usually in that process there are multiple versions of that data that are put in, right? So according to Rubin's rules, we might impute 18 different ways or whatever it is. And so the uncertainty in our imputation is passes through to our estimates or classifications or whatever it is we're doing. Is that part of your process as well?
I think that's definitely actually but how I thought of it for this stage of the process was being somewhat agnostic to that and just trying to maximize our F1 score. And so I guess I think it's an issue, but to me it's orthogonal to what we're trying to accomplish in the paper.
Well, so just thinking of like a toy counterfactual case, imagine I just had one bomb crater, right? Literally, I had one good picture of a bomb crater, and then tons and tons of pictures of non-bomb craters. And what I did was I took that one picture I had and just added a ton of noise to it over and over again, and I made 500 copies of that bomb crater, all of which had noise in them. Mm-hmm. When it came time to do the classification on the test data set, really all I'd be doing is just matching to that one crater, right? And so what's the advantage of adding in the noise in terms of getting better predictive accuracy rather than simply just matching to the original crater?
So I'll address it in two parts. For the bomb crater paper specifically, we had testing training data, and then we just did some out of sample across the entire satellite image. So we were able to validate actually to see that it was accurate. And basically we're adopting a similar approach for what we're doing here, where we have testing training data that we worked on, and then we did out of sample prediction just to see how good the F1 score was. So I think that it's the issue with just having one image and adding a lot of noise to it. To me, that would potentially be a problem with overfitting as well. Although I am curious about extending this process to looking at starving the machine learning algorithm to see how low how many true positives we actually need to have good forecasting out of sample.
For the other paper, Soren, Andrew, and Hannah, I was really curious about the applied the application of these methods. Some of them I've seen before. For example, the partial dependence plot I think is pretty commonly observed in these sort of models. I'm kind of curious about the application because it seems like what you guys were reporting was the probability of being of a certain race if you were killed. Is that correct? Am I correct in thinking that?
Sorry, it took me a second to get to the unmute. Yeah, so it's the probability that the decedent, so the individual killed by police, is either a white person or a black person.
Right. So that's the conditionality is on dead, right? And then you're doing the probability of the race giving dead. But just thinking about the sort of national conversation that's happening right now in the United States, it seems to me like the real debate is actually over probability of kill given race, right? The idea being that African Americans are a relatively small proportion of the population. So like if the police were sort of really being fair, there would actually be way more white people getting killed in all categories because we just make up a greater proportion of the population. And so I'm wondering if you needed to sort of reverse that that inference and talk about, what's the probability of an encounter being deadly? How would your techniques be able to answer that? Would you need different data or what?
Yeah, that's a good question. My initial response is that we might be constrained by the data, like we might need different data. But Soren and Andy, jump in if you feel like you have any ideas on how we might alter our techniques to answer that question.
Yeah, so like I get what Justin's saying. I'm reminded of what the Knox and Momolo comment on whatever that other paper was.
So they're fighting on Twitter or something.
Yeah. So we won't jump into that. So I mean, really, this is our replication data from Streeter's 2019 paper. But I agree with you, and this is what we were talking about yesterday. Is it's strange thinking about race as a dependent variable, and interpreting it was awkward. So I think the paper was much more of like the characteristics of the officer, and then also the decedent as well, and then like the situations. But yeah, I totally agree. So.
Well, so I'm also I'm a little curious about, so stepping back from the specific presentation technologies that you're talking about, which are really about sort of getting a finer grained picture of relationships that are in the data, sort of stepping back because this is framed in terms of drawing causal inferences. And of course, there are lots of barriers to causal inference, and machine learning techniques don't necessarily take all of those techniques head on. All those problems head on. So, for example, a machine learning technique is probably not going to solve a confounding problem if the confounding variable is not in the data, right? And conversely, if you have a collider, which is creating a relationship where none really exists, I don't think anything about the machine learning algorithms that are typically applied, like neural networks, is going to recognize that and pull it out. It's just going to report the relationship. And my usual kind of spiel on this is that machine learning techniques are basically fundamentally focused on solving the problem of incorrect specification, right? It allows a lot more flexibility in specification. So I'm curious, like, is there more to what you're saying in terms of machine learning's ability, when properly applied, to overcome these other problems, or is it just really about the specification?
So I think like the causal inference machine learning, like combination is still at the very early stage. I was reading, there's a really interesting paper by Zhao and Hasty in the Journal of Business and Economic Statistics from 2019, where, kind of trying to like bring these two fields together. So I think overall, like, we're not really trying to wade into that. It's more of like, here's a new, here's several graphical approaches, here's their advantages and disadvantages. I think the AL plot, like Soren was talking about, I think is convincing in a lot of ways due to the, these sort of distributional issues that we talk about. I don't think it wouldn't address the causal issues that you talked about as well, though. But so.
We actually have a couple of questions that have come in from the audience, so I'd like to read those. First, for the Edgerton paper, this is from Heron Cho. This might be more of a substantive question than a methods one, but do we know whether public opinion variables fare better than the usual predictors of terrorism? And then for the Jordan et al. Paper, well, we'll do them in sequence. So first, let's do the Edgerton paper.
So some of the survey questions and public opinion data correlated with the terrorism TV in a way that I have to think about it more and look at what variables are coming out. But the best Gallup World Poll data was, are you afraid of terrorism? And on predicting if there was a terrorist attack that year. So I need to, some of the survey questions did really well, but I'm not sure how meaningful the relationship is.
Yeah, and some of the items that we thought may have predictive power would be views of the government, such as approval rating of the leader, but also trust in key institutions, things such trust in the military, national government, police. Those didn't seem to have a major impact. So that's one of the things we're going to look into, and in the final analysis, kind of have a more clear assessment of where some of the public opinion variables land compared to some of the other key predictors from the literature.
For the Jordan et al. Paper, and this is from the same audience member, Heron Cho, can you talk about the merits of an ALE plot over a partial dependence plot? Again, in particular, the comparison between the two for the 2019 GOP data looked quite similar.
Sure. So I think depending on the relationships that exist between the X sub S, what we are calling the predictor of interest, and the other predictors in the model, if they're sort of unrelated to a lot of the other predictors in the model, it might be the outcome that those plots end up looking similarly, because the issue that the AL plot is fundamentally trying to resolve is if there's a relationship between X sub S and other X's, and if there is, then it might be the case that what looks like a plot that is showing an effect of X on the prediction value of Y as some value of X increases is really just showing what happens as some other X that's not in the plot is also moving up, right? And that's really the leverage, I think, behind why the AL plot exists and what it thinks of itself as being very good at doing, is trying to obviously not control for, but account for the other predictors that are in the model when you're really trying to isolate the effect of one X sub S, which I think also sort of brings a holistic into the conversation we're having on whether this is really about causal effects or not. If you sort of think about the ladder of what the plots look like, they're sort of incrementally trying to further address the other X's, which, like, in a sort of bizarrely basic way, we could think of as being trying to get at the causal effect of just one X at a time on Y. Obviously, that's not like what the model itself thinks of itself as doing, but the plots, I think, are trying to get at a finer grained approach to that question.
So an anonymous attendee has asked concerning the second presentation, this is the Edgerton and Buckles paper, how did the bias variance trade-off factor into your final model, and could you tell us a little bit more about your approach regarding feature selection?
Sure. So at this stage of the project, what we were just concerned was trying to maximize our F1 score. So I didn't really look too much into the trade-offs for the model selection. It was just which one was performing best. And as far as the feature selection, I noticed when I was preparing the presentation that there's definitely some issues. I think there's some potential issues with correlation between our variables. And I think for a second pass, we'll do a dimension reduction approach to try to compress some of the information. And then specifically about the random forest algorithm we used, I think we used, they were weak learning trees with a random selection of variables about 500 times. So the algorithm basically randomly selected a certain number of features in each iteration.
I don't know if this is from the same anonymous attendee, but it's from an anonymous attendee. From the other forecasting models and based on common sense, we know that the key predictor of terrorism or mass killing is the presence of an event in the year prior, which is sort of the corollary to always predict nothing will happen. Then if something happens before, predict the same thing will happen tomorrow. If there was a terror event in the year prior, then a respondent is more likely to be afraid of a terrorist attack. So what's the value added of including public opinion data?
I think that's a really good question. And it's just something that I haven't really looked into at this stage of the project.
Well, we've answered all the submitted audience questions, and so I think I'd like to thank our presenters for being here today and giving us their presentations. I'm going to remind everyone that their presentations will be posted to our website shortly after this broadcast if you want to share them with a colleague or watch them again later. Finally, I want to invite you to join us next week on Friday, July 3rd, when we will host a talk entitled Tweets and Completes, Measuring Individual Level Political Attitudes Using Survey Matched Tweets. That presentation will be from Hao-Han Chan and Brian Gui, both of Duke. We will also host a talk from Albert Chu and Yiqing Xu of UCSD and Stanford, respectively, entitled Bayesian Rule Set, a Quantitative Alternative to Qualitative Comparative Analysis. Please see our website, www.methods-colloquium.com, to get more information about these talks. Everybody, thanks for being here today. I appreciate your presentations and hope to see you next week.